So there's a numbers part to this, and this is one of the numbers part to it. Solubility is basically usually the grams of something that will dissolve in 100 grams of solvent. So the grams of solute that will dissolve in a certain amount of solvent. Okay, and of course it is temperature dependent, so the temperature needs to be given. So let's see, before, has some other videos. So these aren't numbers, but just in general terms, we could talk about something being very soluble or soluble, moderately soluble, slightly soluble, and insoluble. And there's no numbers here, but just in general. And if you look up, Gen Chem 1, I show you guys the Merck Index or the CRC Handbook of Chemicals. But basically it's this thick book that's got about everything you'd ever want to know about elements and compounds. And there's one column for compounds that says what its solubility is, and a lot of times they just say SOL for soluble, SL, slightly soluble, MOD, SOL, moderately soluble, INSOL, insoluble. So the example, anytime you see a sludge at the bottom of a mixture of a solid and liquid solvent, solid solute, think that it's saturated. So basically at that point, the most amount of solute that can go into solution is in, okay? And it is temperature dependent. So the example with the salt, the simple example, dissolving salt in water that they showed before, when they added a little bit of salt, it all went into solution. That was actually unsaturated. How do we know that? Because we could add some more salt, and it went into, it disappeared. Okay, so an unsaturated solution can take more of the solute to be dissolved. A supercalifragilisticexpialidocious, no, a supersaturated solution, I always think of that, is one that is, it's unstable, supersaturated. It means basically you have, for one trick or another, been able to put more solute in the solvent than it ought to be able to hold. Okay, it's supersaturated. And like I said, it's unstable. We're going to see, I think, an example coming up. Okay, so things I'm hoping you get from maybe this slide and kind of this discussion is this whole dissolving and precipitating is kind of a dynamic process. So here we have kind of a fresh lump of solute down at the bottom of this beaker, and we see it's dissolving. Okay. Notice that at some point, once it starts to kind of gain some progress with dissolving into the solvent, the solute begins precipitating. And precipitating here is called crystallization. Crystallization and precipitating is the same thing. And is it starting to look like an equilibrium? Well, definitely we're building up to equilibrium. Equilibria, I think, is unit 3 in here, this class. But by definition, an equilibrium is where you basically have something going from left to right and something going from right back to left again in equal amounts. So the significance of C there is you have the same amount of dissolving as you do crystallization or precipitation. So the particle, put another way, the particle that's in solution won't always be in solution. It kind of cycles to crystallize, and you know what I'm saying? It's dynamic. This is a good one. This could be a practical use. All right, so this is where I told you, it seems to me that if I wanted to get a solid solute, dissolve it in a liquid water, I'd heat it up, but not always, okay? We're going to see that that's usually the case, but not always. So if we kind of put the whole dissolving process in an equation like this, we start with the individual solid we want to dissolve, that's the solute, and the solvent, okay? And our goal is to go ahead and make a solution out of it, to dissolve the solute in the solvent, right? So when it's at equilibrium, this is the sort of thing we have, Okay, so not like, it's like you saw C in the figure a few slides ago. Figure C is where not only do we have the dissolving process, but we also have the crystallization process. Well, basically, the solute in the saturated solution is coming out and going back into the sludge again, okay? But it just kind of keeps going. So it's in equilibrium. All right. So, if we change the temperature, do we get more solute going into solution? Do we get more stuff dissolved? That's the question, okay? So, in these next few slides, if we make it warmer, okay, we try to heat it up. Heat is going to be on the reactant side. Add heat, all right? Increase temperature. If we cool it down, then actually we're going to be, can't remember if we put heat on the product side or removing heat. So each one of these lines is a different substance, a different salt. Remember, salt is just an ionic compound, okay? So we have potassium perchlorate, potassium sulfate, potassium nitrate, ammonium chloride, sodium chloride, and lithium sulfate. So each line is different. So what you're seeing here along the y-axis is how many grams go into 100 grams of water. Okay. Along the x-axis, you see the different temperatures. So actually, if you want to put homework here, you can, because you're going to be using this slide. You probably get it from your textbook, but you'll be referring to this in your homework. So if we pick on potassium perchlorate down there, okay, we have, if we just kind of pick here at 50 degrees Celsius, okay, we have a region here and a region under here. Okay, region 1 here says that actually this would be, if you're up here, this would, how do I say this? Point S is saturated. So what do you think? Let me pull up my marker here. You guys see what you think, how many grams of potassium perchlorate? I don't know. Let's maybe 6 grams of potassium perchlorate at 50 degrees is saturated. So that's why then this region 1 is supersaturated, SS, okay? And this down here is unsaturated. Does that make sense? At that 50 degrees. Yeah, I think so too. I like it when things make sense. Okay. So, can you see what's different about lithium sulfate? It's going down. It's got a negative slope. So this is why I was saying that lithium sulfate is one of those where if you heat it up, it's going to become less soluble. See how that is? Ammonium chloride was one of those that had a positive slope. Okay. So this is in, this is like at room temperature, and this is iced down. The same amount of water and ammonium chloride is present in both, but here ammonium chloride is just less soluble, okay? So you see it precipitate out. So the whole dissolving process, it's always more complicated than you think, right? We can kind of think it in steps. Remember how Hess's law is basically, if you can describe a process in a number of steps that all add up to equal the process, then you're cool with that. That's what this kind of reminds me of. So we have, what does a positive delta H mean? Is it endo or exo? Endo, that's right. It means here we still have to bump it with 2 kilojoules of energy per mole to go ahead and ultimately get this potassium fluoride to dissolve. Okay. Yep. But they're not all endothermic. Okay, here's the potassium fluoride, and I can't, seems like I've got some slides here that they don't always agree on the enthalpy of dissolving, so. But again, you can kind of think of it stepwise. See, this one has it as a negative, and the other one has it as a positive. Oh, didn't it? Yep. It's the same stuff. I cannot explain it. Is the other one potassium fluoride too? Yep. I'll try to track it down one of these days. Because check this out. The enthalpy of dilution or solvating, okay, the enthalpy of dissolving is -16 instead of +2. We ran into an issue today in meteorology too, where I was like, dude, they got the figure wrong, you know. So I'll try to track that down. But aside from that, so the first step is basically breaking those ion bonds, okay? And that's always going to be positive because it's endothermic. Breaking bonds requires energy, okay? And this is looking at dissolving salt, sodium chloride. And you're always going to have a positive energy for basically those little water molecules surrounding the cation and anions, okay? But the question is, what do you get at the end when you add all of these up? Is it going to be positive, so it's going to be endothermic, or it's going to be negative, so it's going to be exothermic? So these are individual ions when it comes time for sticking water molecules around them, how much energy is released. I don't think I'll use that one for your homework. So here's the deal. I did not look at these, but let's look at them. I mean, I don't have a thingamabobber. But I'm trying to think how all right. Stress. I love the subject because it's like so near and dear to our hearts. It's like if you stress anything, if you poke at it long enough, it's going to give you a response. That's almost like one of Newton's laws, that for every action there's an opposite and equal reaction. The Chalais's principle. Yeah. So the stress basically takes the equilibrium out of whack, and a new equilibrium is established. It adjusts. It's a poke. Boy, I left lots of words off for that one. Chalais's principle. And I've heard it pronounced so many different ways, so just feel free to correct me. So chemical equilibria are great at looking at Chalais's principle. So do you see at the top there, the H2 plus the I2, okay, goes to form 2HI, but 2HI also goes back to form H2I2. That's an equilibrium, the back and forth, okay? So, and we'll be talking more about chemical equilibria, okay? But this doesn't have to do with Chalais's principle. This is talking about a chemical equilibrium. So the way you read this is kind of, it's a reaction progression. I think it even says that. So basically time is going along the x-axis from left to right. So what they're saying is they started out with 0. By the way, what do the brackets mean? Molarity, yep, with an R, yep. So they started out with 0 HI, which we still are going to call the product, even though it's back and forth. And they started out with all the same equal concentrations of H2 and I2. Okay, over time, you expect the H2I2 to go away and form the HI, and it does. But basically, when the dust settles, that we can see the equilibrium concentrations, and I don't know where they start, but just in general, these are equilibrium concentrations. Deadpan. What's that mean? Their molar concentrations are constant. Is it going back and forth? Yeah. But are the molar concentrations constant? Yeah. So equilibrium, that's what we mean by equilibrium. This is also another way to think of equilibrium. Basically, what you have a liquid here that is going to evaporate, go from a liquid to being a gas in this headspace here, this nice little bell jar over it. So first you have all evaporation, then you have evaporation and condensation, okay? And then, but still more evaporation than condensation. And here, see, you have equal. If you were to count the little up arrows, they're equal to the little down arrows. So this is equilibrium. And another equilibrium, not chemical equilibrium, but that's just like physical phase equilibrium. Of course, we talked about this equilibrium. So those are three different equilibria that the Chatelier's principle says, take a system that's equilibrium, give it a poke, and see what happens. But it's not as random as wonder what's going to happen. We're going to talk about how you can tell what should happen. Okay, we'll talk more about Le Chatelier's principle later, but just to kind of introduce you to it now. So what sort of stress, what do we mean by a stress? Well, a stress could be sprinkling in some of the reactant of the product, mixing it up, right? You put it out of equilibrium, like that first one with the H2, the I2, and the HI. Sprinkle some in, see what happens. Okay, you could monkey with the temperature, and that will have consequences. That one with the bell jar, you know, if we were to go ahead and jack up the temperature of the liquid, we'd reach a different equilibrium vapor pressure, wouldn't we? Monkey with the pressure has consequences. Okay. So back to the whole dissolving thing, that equilibrium where you have sludge at the bottom is what I think of. And basically, it's an equilibrium with going from dissolving to crystallizing or precipitating. Okay. So, what effect? You know that figure here, do for your homework. If you add heat, the effect it has on the dissolving process depends on if the overall dissolving process is exo or endothermic, and I'll show you how that works. Okay. So let's say that it's endothermic. Let's say the overall process to get something to dissolve, you've got to add heat. Well, if that's the case, we're going to put heat on the reactant side because you have to put it in. So we're going to put it on the reactant side. All right? So here is your endothermic dissolving process. Heat's on the reactant side. Okay. So according to Le Chatelier's principle, and again, this is kind of an introduction to it for later, if you poke it, I just now thought of that this semester, if you poke it on the reactant side, it's basically going to make it go from the reactant to the products. You poke it. So if it's endothermic, it is going to make more solution happen. And what is solution? This is the dissolved part. Okay. So only when a solid is in dissolving solid is endothermic will you increase its solubility by increasing the temperature. You'll get a new amount dissolved, new equilibrium. That's an example of Le Chatelier's principle. Poke. I never have figured out what poke means on Facebook. I think it's come and gone, I don't know, and I missed it. So, but you know what's coming up next is what if it's exothermic? What if energy is released instead of required? Well, okay, so this is not there yet. So the solubility of a solute will increase if you increase the temperature if the dissolving process is endothermic. Okay. There we go. Exothermic, and I'm still going to have to find out if potassium fluoride is if it's endothermic by 2 kilojoules or whatever, kilocalories, kilojoules, or if it's exothermic by, was it negative 18 or something? It's like, dude, somebody look that up for me. Okay, so if heat is released, we're going to put heat on the product side, right? There we go, exothermic. And if we poke is opposite of the tug of war. So if we poke it, increasing the heat, increasing the temperature, poke it by adding heat, increasing the temperature. Notice we're going to get it to break back apart again. We're going to get more sludge. This was the case with lithium sulfate. Increased temperature, decreased solubility. Poke. So it's not that, oh, and by the way, while you're writing that down, the way I think of it is, it is out of equilibrium. It's out of whack. You could basically screwed up the equilibrium by heating it up. And so when I look at the pair of reaction arrows in the middle, the equilibrium arrows, I think of it like this momentarily, that basically the amount going this way from, let's see, I guess that's from right back to left, is greater than the amount going this way, just temporarily. Okay? And it will eventually reach a new equilibrium. It will have a higher amount of in this case, of sludge at the bottom. Oops. Okay, so in general, if the dissolving of a solid is exothermic and you heat it up, get ready to have more sludge. Okay, its solubility will decrease if it's exothermic. So we talked about, that is just something. I'm going to have to report that. It is having a bad day. So we talked about adding heat. Lowering the heat is the same thing as, let's see, lowering the temperature is the same thing as removing heat. It's the opposite of a poke. If you remove heat, basically, then you have more pulling than a poke. Okay? I don't think it'll start on this. Let's see, what else we got? Is the next one you say the effect of temperature on solubility of gas or not? Well, I think that's a sign. We'll pick up here. We'll just knock out these last few slides. It's kind of fun to finish up on the Chatelier's. And